Welcome to this coding walkthrough. In this session, we'll dive into LeetCode problem number 8, string to integer, atoi. This is a classic string manipulation problem that tests your ability to parse input while handling a variety of edge cases. Let's explore the problem, break it down step by step, and develop an efficient solution. Let's get started. In this problem, our goal is to implement the function myatoi, string s, which converts a string into a 32-bit signed integer. This function is very similar to the catoi function, which handles string-to-integer conversion based on certain rules. The rules start with ignoring any leading whitespace characters in the string. Next, the function looks for an optional sign, which could be a plus or dash to indicate whether the number is positive or negative. If both signs are present or a non-numeric character appears at this stage, the conversion stops immediately. The next step is to read consecutive numerical digits to form the integer. If the function encounters a non-digit character or the end of the string, it stops processing further. Finally, if the resulting number exceeds the range of a 32-bit signed integer, which is from -231 to 231, the function returns the nearest boundary value within that range. When it comes to handling the boundaries, the function will return -231 if the converted integer underflows, and 231 if it overflows. Additionally, if the input string is empty or contains only invalid characters, the function should return 0. The input for the function is a single string s, where the length of the string is between 1 and 200 characters. The output is a single integer that represents the converted 32-bit signed integer value. To help clarify these rules, let's look at some examples. In the first example, the input string s is simply 42. The function outputs the integer 42 because there are no leading spaces, no sign, and the string consists only of valid numerical digits. In the second example, the input is -42. Here, the leading whitespace is ignored, and the dash sign indicates that the number is negative. The function then reads the digits 4 and 2 consecutively to form the integer 42, and applies the sign to get a result of -42. In another example, the input string is 4193 with words. The function processes the numerical part of the input, which is 4193, and stops when it encounters the first non-digit character, which in this case is the letter W. The valid integer 4193 is returned, as the function halts further processing at that point. Now, consider the example where the input string is words and 987. In this case, the string starts with non-numeric characters, specifically the word words. Since no valid integer can be formed from this input, the function returns 0. Another interesting scenario is when the input string is -91283472332. The function identifies the number as negative due to the dash sign, and processes the digits to form the number 91283472332. However, this value exceeds the lower limit of the 32-bit signed integer range, which is -231. As a result, the function returns the closest boundary value, which is -231, or -21474836648. The explanation for these examples highlights how the function handles different edge cases. For instance, if the input string starts with non-numeric characters, as in words and 987, the function recognizes that no valid integer can be formed and simply returns 0. Similarly, for the -91283472332, the function ensures that numbers exceeding the 32-bit range are clamped correctly to the nearest boundary value, in this case, -21474836648. These examples underscore the importance of adhering to the defined rules for handling various types of input, including strings with leading whitespace, optional signs, and numerical digits. The constraints for the problem specify that the input string will have a length between 1 and 200 characters. The function must properly handle leading and trailing whitespace, as well as optional signs like plus or dash. Additionally, it needs to account for integer overflows or underflows by returning the nearest boundary value, either -231 or 231. If no valid conversion exists, for example, if the string contains only whitespace or no digits following a sign, the function should return 0. Let's examine a few edge cases to further clarify these requirements. For an input like, which contains only whitespace, the function should return 0 since no valid integer can be formed. Another edge case occurs when the string contains only a sign without any digits, such as dash or plus. In these cases, the function should return 0 because a sign alone does not constitute a valid integer. Similarly, if the input exceeds the 32-bit integer range, such as 21474836648 or -21474836649, the function must handle overflow and underflow by clamping the output to 21474836647 or -21474836648, respectively. Finally, if the input has non-numeric characters mixed with digits, like ABC 123 or 123 ABC, the function should either return 0 or stop parsing at the first invalid character to return the valid portion of the integer. These edge cases ensure the implementation is robust and handles all possible inputs correctly. When tackling the problem of converting a string to an integer, commonly known as atoi, it's crucial to recognize the various edge cases that can occur. For instance, you may encounter strings with leading spaces, optional plus or dash signs, or even characters that disrupt the parsing process. One approach to solve this is the brute force method. Here, you process the string character by character, manually converting valid digits into an integer while ignoring invalid parts. While this method is conceptually simple, it can quickly become cumbersome due to the large number of edge cases you need to handle, such as clamping the result for overflow or parsing strings with mixed characters. Additionally, this approach can result in repetitive and error-prone code, making it harder to scale or maintain. On the other hand, a more refined solution involves using a single-pass parsing method coupled with state management. This optimized approach systematically handles each part of the process, skipping leading whitespace, identifying signs, extracting numeric characters, and clamping values to stay within the 32-bit signed integer range. By addressing each of these concerns in one pass, it ensures efficiency and clarity without the pitfalls of repeated string manipulations. Another possible solution to the problem is to use regular expressions. With regex, you can define a pattern that captures a valid numeric substring, including an optional sign, directly from the input string. This approach can eliminate the need for manual state management, simplifying the implementation. However, regular expressions come with their own trade-offs. For one, while they are concise and relatively easy to write, they can be slower in some scenarios, especially with complex patterns. Additionally, regex alone cannot handle all the requirements of the problem. For example, you would still need to separately implement logic for handling overflow or clamping values. Considering these factors, the optimal choice is the one-pass parsing method with state management. It provides a structured way to handle all edge cases while staying efficient. The intuition behind this solution lies in its step-by-step approach. By skipping unnecessary characters like whitespace, correctly identifying signs, and halting at invalid input, you maintain both correctness and simplicity. Overflow handling is integrated seamlessly during parsing, ensuring the solution is both robust and clean. This method avoids reliance on external libraries like regex and gives you full control over the parsing logic. In terms of trade-offs, the chosen approach strikes a good balance across several factors. From an efficiency perspective, it operates with O(n) time complexity, as each character in the string is processed exactly once, and it uses O(1) space since no additional data structures are required. While this method might involve slightly more effort to implement compared to using a regex-based solution, it is far more robust and adaptable to changes in problem requirements. For example, if additional constraints or features were introduced, the state management approach could be extended without significant rework. Its flexibility and systematic handling of edge cases make it a reliable and scalable choice. Overall, this method ensures that the solution is efficient, clear, and well-suited for real-world applications, where robustness and performance are key considerations. To begin solving this problem, the first step is to handle any unnecessary whitespace in the string. Leading or trailing spaces are irrelevant for parsing a number, so we can use the strip method to remove them. This ensures we're working with a clean input. If the string becomes empty after trimming, there's no valid number to parse, so we can simply return 0 at this point. Next, we need to check if the number has a sign. A valid number may start with a plus or dash to indicate whether it's positive or negative. Here, we examine the first character. If it's a plus or dash, we record the sign as either +1 or -1 and move on to the next character. If there's no sign, we assume the number is positive. However, if the first character isn't a digit or a valid sign, the string doesn't represent a valid number, and we return 0 right away. Now that we've handled whitespace and the sign, the next step is to extract the numeric portion of the string. Starting from the first character, or the one after the sign, we iterate through the string to collect consecutive digits. If we encounter a non-numeric character, we stop parsing immediately. These numeric characters can be stored in a temporary list or directly appended to a result variable. If no digits are found after the sign, there's nothing valid to parse, so we return 0. Once we've gathered the numeric portion, we convert it into an integer. This is straightforward using Python's built-in int function. To ensure the correct polarity, we multiply this integer by the sign we recorded earlier. After converting the string to an integer, we need to ensure the result fits within the signed 32-bit integer range, which spans from -2 to the power of 31 to 2 to the power of 31, 1. If the value exceeds this range, we clamp it to the nearest boundary. For instance, any value greater than 2 to the power of 31, 1 should return 2 to the power of 31, 1, and any value less than -2 to the power of 31 should return -2 to the power of 31. Finally, after all the processing, we return the computed and clamped integer as the result. This ensures the output adheres to the problem's constraints and handles edge cases where the number might fall outside the valid range. When solving this problem, it's important to consider a few key insights. First, there are several edge cases to handle. For example, if the string contains only whitespace, the result should be 0 since there's no valid number. Similarly, if no digits follow a sign, such as with the input plus, we also return 0. For strings with mixed content, like 42 ABC, we stop parsing at the first non-digit character and only consider the numeric portion. Lastly, if the number exceeds the 32-bit integer range, we clamp it to the defined limits. In terms of efficiency, this algorithm processes the string in a single pass, giving it a time complexity of O(n). Operations like trimming whitespace and clamping are constant time, O(1). The space complexity is also O(1), since we use only a few variables to store intermediate results. Iterating over the string character by character is critical because it allows us to handle mixed content and invalid characters seamlessly. To implement this algorithm, we rely on a few simple data structures. The input string is processed directly to allow for easy character-by-character analysis. We use an integer variable to accumulate the numeric value and store the final result. Additionally, a signed variable, which can hold either +1 or -1, helps track the polarity of the number. To optimize the solution, we employ some early exit strategies. For instance, if the string is empty or invalid after trimming, we immediately return 0, avoiding unnecessary processing. Another optimization involves clamping the number to the 32-bit range during parsing, instead of waiting until after the full integer conversion. This prevents overflow and keeps the algorithm efficient. Together, these data structures and optimizations ensure the solution is both robust and performant. Here, we begin by defining the myatoi function inside a class named solution. The first step is to handle any leading or trailing whitespace in the input string s using the strip method. This ensures that the string is clean before we proceed. If the resulting string is empty, we return 0 immediately, as there would be no valid number to process. Next, we check if the number has a sign, either negative or positive. We initialize sign to 1, assuming the number is positive. If the first character is a minus sign, we set sign to -1 and move the pointer I forward by 1. Similarly, if it's a plus sign, we keep sign as 1 and also increment the pointer. Now, we start converting the characters in the string to digits. We initialize a variable number to 0, and as long as the current character is a digit, we multiply number by 10 and add the integer value of the current character. This builds the number one digit at a time. Once we're done processing the digits, we apply the sign to the number by multiplying number with sign. After determining the signed integer, we need to ensure that the result stays within the valid 32-bit integer range. We define int_min as -2 to the power of 31 and int_max as 2 to the power of 31 minus 1. If the computed number is less than int_min, we return int_min to avoid underflow. Similarly, if the number exceeds int_max, we return int_max to prevent overflow. Finally, if the number is within the valid range, we simply return it as the result. This ensures that our function handles all edge cases, including whitespace, signs, invalid characters, and range clamping, making it robust and reliable. Here, we start by defining the myatoi method, which takes a string s as input. The first step is to handle any leading or trailing whitespace by using the trim method. If the resulting string is empty, we immediately return 0, as there's nothing to process. Next, we determine if the number represented by the string is negative or positive. We initialize a variable sign to 1, assuming the number is positive by default. If the first character of the string is a dash or plus, we adjust the sign accordingly and move the index I forward to skip the sign character. After this, we start converting the characters into digits. We use a long variable number to handle potential overflow during the computation. Inside a while loop, we check if the current character is a digit using character.isDigit. If it is, we multiply number by 10 and add the integer value of the current digit. To prevent overflow, we add checks to return integer.min_value or integer.max_value if the signed value of number exceeds the range for integers. Finally, we increment I to process the next character. The loop continues processing the digits in the string until a non-digit character is encountered or the end of the string is reached. Once the loop exits, the method proceeds to the final step, which is to return the result. We apply the calculated sign to the number variable and cast it to an integer before returning it. This ensures that the final result is correctly signed and within the bounds of a 32-bit integer. With this implementation, the myatoi method is able to handle edge cases like leading whitespace, optional signs, and integer overflow, making it a reliable solution for converting a string to an integer. Let's start with the first example, where the input string is 42. The function begins by taking the input string and initializing it as s equals 42. In the first step, we strip any leading or trailing whitespace using the strip method. Since there are no spaces in this case, the string remains unchanged as s equals 42. Next, we handle the sign. The first character is checked, and because it is neither a dash nor a plus, the sign is assumed to be positive, so we set sign equals 1. We then move to the third step, which converts the numeric characters to digits. In this step, a loop iterates through the string as long as the current character is a digit. First, at index 0, the character 4 is processed, updating number to 4. Then, at index 1, the character 2 is processed, updating number to 42. At this point, we've reached the end of the string, so the loop exits. The final value of number at this step is 42, and the index is now 2. Now, we move to step 4, where the sign is applied. Since the sign is 1, the value of number remains 42. In step 5, we check whether this number falls within the 32-bit signed integer range, which is from -2 to the power of 31 to 2 to the power of 31, 1. The value 42 is well within this range, so no adjustments are needed. Finally, the function outputs the result, which is 42. In the second example, the input string is -42abc. The initial string contains leading spaces, so after applying strip, the result becomes s equals -42abc. Next, we handle the sign. The first character is a dash, so we set sign equals -1 to indicate a negative number, and the index is increment to 1. In step 3, we start converting numeric characters to digits. The loop begins at index 1, where the character 4 is processed, and number is updated to 4. At index 2, the character 2 is processed, and number becomes 42. When the loop reaches index 3, it encounters a non-digit character, and exits. At this point, the final value of number is 42. Next, we apply the sign in step 4. Since the sign is -1, the value of number becomes -42. In step 5, we verify that -42 is within the 32-bit signed integer range, so no adjustments are necessary. The function then outputs the result, which is -42. In the third example, the input string is 4193 with words. The initial string doesn't have any leading or trailing spaces, so strip doesn't change it, leaving s equals 4193 with words. Moving to step 2, the first character is a digit, so the sign is set to 1. In step 3, we begin processing numeric characters. At index 0, the character 4 updates number to 4. At index 1, the character 1 updates number to 41. At index 2, the character 9 updates number to 419. Finally, at index 3, the character 3 updates number to 4193. When the loop reaches index 4, it encounters a space, which is not a digit, and the loop exits. At this point, the final number value is 4193. In step 4, we apply the sign. Since the sign is 1, the value of number remains 4193. In step 5, we check whether 4193 falls within the 32-bit signed integer range. The number is within range, so no adjustments are necessary. The function then outputs the final result, which is 4193. The time complexity of our solution is O, n, where n is the length of the input string. Let's break this down step by step. First, the operation s.strip removes leading and trailing whitespace from the string. Since strip needs to check every character in the string, its complexity is O, n. Next, checking whether the string is empty, which is done using if not s, is a constant time operation, O, 1. Parsing the sign involves checking if the first character is a plus or dash, which is also O, 1. The most significant contribution to the time complexity comes from the while loop. This loop processes numeric characters and iterates through them one by one. Each iteration involves constant time operations, such as checking if a character is a digit, converting it to an integer, and updating the number. Since the loop iterates through all numeric characters in the string, its total contribution is O, n. These components together result in an overall time complexity of O, n. When clamping the result, we check if the number is less than the minimum integer or greater than the maximum integer. These are simple conditional checks and are executed in constant time, O, 1. By combining all the operations, the dominant contributors to the time complexity are the strip, function, and the while loop, both of which are O, n. Therefore, the total time complexity of the solution remains O, n. Moving on to space complexity, this algorithm uses O, 1, space. The input string is passed as an argument to the function, and its storage is external, so it doesn't add to the space complexity. When we use s.strip, it creates a new string without leading or trailing whitespace, but this new string replaces the original in memory, so no additional space is used. Finally, the variables used in the function, such as I, sign, number, and others, occupy a fixed amount of space regardless of the input size. This keeps the space complexity at O, 1. Because this solution avoids using any additional data structures, the overall space complexity remains O, 1. Let's consider how this compares to a naive or brute force approach. A less optimized solution might involve creating intermediate substrings during parsing, for instance, by slicing the string or using regular expressions. This would lead to an increased space complexity of O, n, as these intermediate strings require additional memory. Furthermore, if the naive approach processes the string in multiple passes, one for trimming whitespace, another for identifying the sign, and yet another for parsing digits, the time complexity might increase to O, k asterisk n, where k is the number of passes. In contrast, our optimized approach minimizes the number of passes over the string and avoids creating unnecessary intermediate strings. This ensures that the time complexity stays at O, n, and the space complexity remains at O, 1. Analyzing the best, average, and worst cases gives us a clearer picture of the algorithm's performance. In the best case, the input is a single valid numeric character, such as 5. Here, the strip function and the while loop process only one character, resulting in a time complexity of O, 1. The space complexity, as always, remains O, 1. For the average case, consider a string with a mix of whitespace, a sign, and numeric characters, like -123 ABC. In this scenario, the strip function and the while loop work through the input string, leading to a time complexity of O, n, and a space complexity of O, 1. The worst case occurs with an input consisting entirely of digits and whitespace, such as 1 2 3 4 5 6 7 8 9 0 1 2 3 4 5 6 7 8 9 0. The algorithm processes all the characters in the string, resulting in a time complexity of O, n. Regardless of the case, the space complexity remains O, 1, throughout. To validate the time complexity mathematically, consider the major contributors. The strip function iterates through all n characters in the input string, contributing O, n. The while loop, in the worst case, also processes all n characters, contributing another O, n. All other operations, such as parsing the sign and clamping the result, are constant time operations, O, 1. Combining these, the total time complexity is O, n, plus O, 1, which simplifies to O, n. On the space complexity side, the algorithm doesn't use any additional data structures. The input string's memory is external, and variables occupy a fixed amount of space. Thus, the space complexity is O, 1. This demonstrates that the solution is both time efficient and memory efficient. When working on the string-to-integer problem, there are several common mistakes to be aware of. First, ignoring leading whitespaces in the input string can lead to incorrect parsing. It's essential to skip these spaces before interpreting the number. Another frequent issue is not handling signs properly. Both the plus and dash signs must be accounted for, and they should be processed immediately after leading spaces. Overflow and underflow are also critical concerns. If the parsed number exceeds the range of -231, 2 to the power of 31, 1, you need to clamp the value to this range to avoid runtime errors or invalid results. Additionally, parsing should stop as soon as a non-numeric character is encountered. Continuing beyond that point is a common source of bugs. Finally, avoid using floating-point arithmetic for intermediate calculations. Precision errors can occur, especially when handling large integers, so sticking to integer-based computations is safer and more reliable. Now let's focus on what interviewers often look for when testing this problem. Edge cases are a critical area. Examples include empty strings, strings that contain only plus or dash, those with trailing or leading spaces, or strings with a mix of valid and invalid characters. Demonstrating awareness of these scenarios is key to impressing your interviewer. A modular approach can also make a big impact, breaking the solution into clear steps like trimming spaces, handling signs, parsing digits, and clamping the final value shows that you have a structured way of solving problems. It's also important to highlight the time complexity of your solution. Since each character in the string is processed only once, your solution should run in O, n, where n is the length of the string. Lastly, discuss how you handle invalid inputs gracefully without causing runtime errors. This demonstrates robustness in your code. For further practice, related problems like LeetCode 65 on validating number formats or LeetCode 7 on integer reversal offer opportunities to refine your skills with similar edge cases. Let's consider some alternative approaches to solving this problem. One robust method is the state machine approach. This involves creating a finite state machine to handle transitions between different states, such as processing leading spaces, identifying the sign, reading digits, and so on. While this method is systematic and minimizes the risk of missing edge cases, it often requires more effort to implement and debug. Another approach is regex-based parsing. By using regular expressions to extract valid patterns from the input, you can simplify the solution significantly. However, regex may be less efficient for very large strings or complex constraints. When evaluating trade-offs, the state machine approach offers greater reliability and control at the cost of added complexity, while regex-based methods provide conciseness but may fall short in terms of performance for certain scenarios. Choosing the right approach depends on the problem requirements and your comfort with these techniques. Great job! We've successfully tackled the string to integer atoi problem by breaking it down and handling various edge cases. Remember, string parsing is a fundamental skill that often comes up in technical interviews. Keep practicing similar problems to sharpen your skills. Thank you for watching, and don't forget to like, subscribe, and stay tuned for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!